So for today, we are going to continue what we discussed earlier on the drawing bendy moment diagrams, basically. So there are lots of confusions how you actually analyze a simple determinate beam or its bendy moment diagram, right? Right. So there can be various type of loads, right? So we will consider one such example, and yes, we are ready to go. If you didn't get the basic concept, please watch the link in the description where I have given a detailed explanation on the basic of drawing a bendy moment diagram from A to Z, right? So please watch that before moving into this video. So this is only a continuation of that, right? So we will consider a beam like, okay, I don't have any preparation, so I will just consider something, let me say like this. A straight beam, okay. Okay, so I will add here a triangular UDL, right? A triangular or even trapezoidal, that's okay. So right, so the entire beam and these 15 meters, right? So I would consider this on how much? Oh, 5 meters. Okay. So here 0 you have load. Here it will increase to 5 kilometer. Okay. So at x equals 8. Okay. I will add what to say. So a bending moment. So I have bending moment of 15 kilometer meters. I would say 20, right? Newton meters. And what else do we need to add? Okay, we will add a uniformly distributed load in this way. How to add? Okay, yes, we will add here. Okay, now we are done. So that's going to be 3 kilonewtons per meter. So this is going to be around, I would say this is 2 meters. This 5 meters. Okay. So just consider, so this beam is going to bend in somehow in a complex manner, right? So we need to analyze its bending. So the first thing is, when you have trapezoidal loading or bending moment, don't be confused. We just need to know how we are going to mathematically uh, idealize this triangular load, right? So within this beam, right, within this part, so we have to consider several parts, right, to construct the overall bending. So in this, within this part, you have overall the same behavior due to this increase in load. So you can just write an equation within this limit. And before you meet the bending moment, you can write another expression compare for this whole part, right? So after meeting you bending moment, so you can consider in this part you don't have anything, right? So you just consider one of that part as well, right? Here also, except for this loading, you don't have anything. So I consider a representative point. I consider a representative point here. I consider a representative point here, right? After the bending moment, right? So here I'll consider, so here within this region, you don't have anything else other than the UDL. So I'll consider 1, 4. So I need 4 equation to mathematically idealize the behavior, right? Okay. If you idealize only from this is not continued after 5 meters. So this is only valid until 5 meters, right? So it's going to be another one from 0 to 8 meters. If you consider this part as well, it is going to be another thing between these points. It is going to be another thing between these 2 points, right? So even we are worrying on uh, within two limits, right? So each so if you consider this part, the equation you are deriving is only valid in this region. If you consider this part, right, so you don't have anything, so you just construct a equation, it is valid in this region. Likewise, for each portion you write an equation, an expression. What you are actually doing is you mathematically idealize the behavior of that each region, and finally you construct each bending moment diagram, and hence you will obtain the final bending moment diagram. That's it, right? So it's very simple when you understand the basic concept. So we shall go ahead. So for the first one, right, I have something like this. X is from, so I'm measuring X from the left end, right? So I'm measuring X from the left end, and yes, I'm taking clockwise positive. You remember left up, right down from the first video, right? So about that. So our x is in between now 0 to 5. Only 0 to 5, this equation will be valid, right? Zero. First, we need to determine the reactions, right? So how to find the reactions? So since there's no horizontal loading, if you consider even consider a pin support, you will have only the vertical reactions only, right? Right. So this is RA, this is RB. So if you consider vertical force equilibrium, RA plus RB is equal to the total load. Total load equals to area of this triangle, right? So it's for 1 meter, it's 1 kilonewton. 2 meters, it's 2 kilonewton. 3 meters, 3 kilonewton the load. So for 1 meter, you increase the load by 1 kilonewton, right? 5 kilonewtons over 5, right? So I will explain that later again. So the total load is the area of the triangle, right? How much you load you have actually. So if you cannot identify, just make a rectangle from this. So that's going to be 5 kilonewton load per 5 meters. So how we are going to take the load? 5 into 25, right? Sorry, 5 into 5. Now you have only half of that. So you just need to divide by 2. So your total load is going to be in the vertical direction. It's going to be 12.5, right? And this is a moment. So fundamentals, this is a moment, not a force. And this is a force, right? 3 kilonewton into 5 meters, right? 3 into 5, it's going to be 50. So that's going to be 27.5. You can take a bending moment about A. Sigma M about A is 0, right? So yes, you can take, so the clockwise positive, so these are out clockwise, right? So the total load is 12.5, and it's acting at the centroid of this triangle. So that's going to be 2/3 of this length. 2/3. If you're going from here, it's 1/3. From here, it's 2/3, right? 2/3 into 5. So that's going to be 10 over 3, right? Plus the bending moment, it's 20, plus the total load 15 into Here you don't need any distance because it's a bending moment directly. Here force, total force into that for the distance where the total force acts. This total force acts from 2.5 from this point, right? 2.5 plus 5 plus 3 plus 2 means 10. So that's going to be 12.5. Equals to RB into how much? 15, right? So if you solve it, so you will ended up with 5, 3, 20 plus 249, right? 249 divided by 15 is going to be 16.6. So this is going to be RA is going to be then 10.8. Right, 10.8, around 10.8, 10.9, right? That doesn't matter. Say this is 10.9. Right. Okay. So now I know the value of R and RA and RB, right? So here you have a force of 10.9, that is RA, right? So you need to cut this beam from distance of X. Right. So if you cut it, you know you have internal shear and bending moment, right? So if you cut here, so I'll always consider clockwise positive, right? This is where we are taking the right hand half, so clockwise positive. You remember left up, right down. So this part, right? It's the left end. For these parts, it's the right end, right? So right, we have to put the shear down, right? It's like this. If you cut it to half, right? So this is your right end of the post, right end of the uh, right end of this part, right? This is your left end of the other portion, right? This is your right end, this is your left end. So if it is right end, you have to put shear in the downward direction, and here you have to put in shear in upward direction, left up, right down. That's my sign convention, right? If you want, you can take other way around, no problem, right? So, but stick to a particular sign convention. That's the advice, right? So we need to take the intensity. That's how we are going to idealize this load. So it's 5 kilonewtons, right? So 10 kilonewtons, 5 kilonewtons. So the intensity Let's say Q, that 5 kilonewtons is for 5 meters. What would be for X distance, right? So that's going to be 1x, right? So literally it's X, right? So if you have X meter length, you have X load. So if you are in 0.5 meters, your load is 0.5 kilonewtons, right? That's how you idealize that load simply, right? So if you have X meters, you have a load of X, right? Load is equal to the length you're acting for this case, right? So the total load would be, okay, the total load is how much? The area of this triangle. So it's going to be the height is X, half time the height time the base, right? Base is also X, right? This is your total load, right? So for that, so that total load is acting at 2/3 of this length. So that is 2x over 3 for a triangle, right? So this is your total W, right? This is going to be, so we can write this way, the moment equation, right? So I can write now. So the moment equation sigma m about this point, I would say this is 1, right? Sigma m about 1 is going to be, you have a clockwise moment of m, right? This shear is not coming. You only consider this half, right? So we have shear from the moment from the shear here, W and R, right? Reaction. So M is gone. So you have a clockwise shear, clockwise moment of 10.9 into X, right? So now we have another one, anti-clockwise. That's going to be anti-clockwise. You remember this point? Around this point, this load is going in anti-clockwise direction. So that's going to be negative. W is this x squared over 2 into the length is 2x over 3. So that's going to be 2x over, sorry, x cube over 3, right? These two are cancelling. 2, right? So you can finally write the equation. Finally write the equation. M is equal to minus 10.9x plus x squared over 3, right? This is the idealized bending behavior, bending moment equation for the first part, right? So now I need to consider this half, because if I go from here to here, nothing happens. So I can take but it's different from here, right? Here, if you go from here to here, the same intensity. So that's why I consider one point between these two, this length, right? So from here, this load is not there, right? So they are a different behavior, but the different behavior is going to be from x equals 5 to x equals 8 until this bending moment is met, right? So I can write like this, from x equals 5 to x equals 8, right? So now total is there. So I have cut it from here, right? This is your x is 5, right? So if you take x distance, so you already have the total weight, total load, right? Of the triangular part, right? Okay. So, and you have a reaction of 10.9, right? So even if we consider all these things, but we derive it, this is valid only for x equals 5 and 8, not valid for this region, right? This is between these points, right? For this region, we have another equation that we derived earlier, right? So it simply says, so I can write, so I can take the value. So left up, right down, you remember. Clockwise, right? So yes, I can write it like this. M is equal to clock. I'll take the clockwise moment around this point. I'll say 2 sigma m around 2 point, right? So m plus 10.9 into x minus this whole thing, right? The total W is, you remember 12.5, right? The total W, the area of the triangle, 12.5, but the distance is, this length is 5, right? Remember, from here, it's going to be how much? And the earlier also, I think we did a mistake. Here we are taking bending moments about this point, right? Here we are taking bending moment about this point. So that's going to be, yes, x over 3. Here it should be x over 3, right? Sorry about that. X squared over 2 is the total load. And the distance is x over 3, right? So we are taking moments about this point. So that's going to be x over 6, right? Right? No, it's okay. So here it's going to be this length, right? So you need to take this length from here. So this is going to be 5 over 3. So that's 1/3 of the length of the load, right? 5/3, sorry, 5 over 3, and you need to, so that distance is, so this is the distance you need, so that's going to be x minus this distance, right? This is 2/3 of 5 over 3. 2/3 of 5, right? 2/3 of 5. So that's going to be 10 over 3. Right? 10 over 3. So yeah, I can write 10 over 3, right? So I took the moment. This is not coming, right? This is okay. This is okay. So I can simplify this. I can simplify this. Minus 10.9 into x plus 12.5 into x minus 10 over 3, right? Okay, so now my second half is okay. I can go to the third part as well. Okay. So you have a reaction of 10.9. You have 5 here, total load, bending moment. And from this cut, you have so this is from the fundamental concept. Don't draw it to here, right? Don't draw it to here. I said don't draw it like this, the bending moment, right? Here, especially at the cut, because you will be confused. Right? It's going to be your M, and this is the total load is again 12.5, right? So you can just write the equation. So now we are mathematically idealizing the behavior between x is equal to 8 to how much? 10. Yes, 10. It's from here, here to here, this region, right? So we did not cut at the bending moment, right? Because here you didn't have bending moment. After passing it, you have the bending moment. So automatically the effect is taken at the boundaries, right? So I can just write the bending moment as this. So the clockwise bending moment, sigma m around this third point, third cut. So that's going to be m plus 10.9 into x clockwise. This is going to be an anti-clockwise 12.5. So it's going to be x minus this distance, right? Again, the same length, right? X minus 10 over 3. It's this distance. That distance is x minus this length, 10 over 3. 5 into 2, 2 over 3. Right? Plus 20. This is a bending moment, not a force, so you don't need any lever arm or anything. So the fundamental is this is already a force multiplied by a distance, right? So that's going to be your final equation. So you can determine m is equals to 10.9x minus 12.5, sorry, plus, this is minus minus 20. So now I'm okay, right? So it's 10.9, 12.5 minus, yes, all things are great. So from the final part, I need to consider what will be the value, right? So please consider it is the same equation like this, right? From the equation number 2, right? What happens is it reduces by 20, right? On this amount, right? So please keep it in mind. On the fourth region, you can write like this. The bending moment is here. So I take some part of the UDL as well. Now x is between 15 to what? 15 and 10, right? So here is 10. Here it's not 15, but in between length, right? So here you have 20. So you have 10.9 and the total load is 12.5, right? So here you have W is how much? You remember? W is 3 kilonewtons. So that means total load is uh, this is x minus 10, right? So the total load is 3 into x minus 10, right? Don't forget that, right? So okay, so I can take a bending moment about this point. So let's consider clockwise positive. So these are the things you need to consider: moment, shear, this load, this bending moment, force, and this, right? So if you are taking a bending moment about this point, sigma m, So again, shear is not coming. So you can simply say bending moment is equal to 10.9 into x minus 12.5 into how much? X minus 10 over 3. That's again the same thing, right? Plus 20. And the total load is, this is anti-clockwise moment. It's going to be negative. So the total load is this, right? And what will be the distance to that? So the total load is this, and it's acting at half of this length. So that's going to be x equals n over x minus 10 over 2, right? So is equal to 0, right? Okay. So the simpler way is also there. You can just cut it from the other end. You can just cut it in from the other end, right? So other end means you can just take this length and consider this is x, right? You can consider this part and write the bending moment equation. So that's very simple because moment, these triangular loads are not coming. That's going to be easy, right? So for now, I'll consider this. Scared. Okay, this is my final bending moment equation for final half, right? So now you can draw this. So to draw this, don't this is you are not, so the whole thing in bending moment is just to for you to idealize the concepts and how to apply that, not drawing these complex curves, right? There are softwares to draw that. Even if you take any software like SAP or Midas, so they will draw it for you. So why that you are learning this? To understand the concept, right? To understand how a particular software idealize the, how you can idealize this, right? To understand that. Your job is not to draw build equation like this and draw the bending moment diagram. Software does it for you, but you should know how the software does it and how you can relate it. Can it be trusted? Can you trust the software, right? So in case of, just in case, if you need to find, you can just idealize something and try drawing it. But drawing is not your main role. To understand the concept, that's important, right? So I will use Excel to draw this. So it's between x is 0 to 5. I have 10 point m is equal to minus 10.9x plus x cube over 6, right? So I can take some values from x is equal to x is equal to, yes, from here 20 moment, right? This is my x. So from here I will draw it from 0.1 intervals, right? Not 0.1. Yes, is it okay? Yes, it will be okay. Yes, here, right? So that's going to 0.1 intervals, right? So x is from 0 to 5, you have one equation, right? You have one equation. From 5 to, so this is going to be overlap at 5, so that's okay. 5 to 8, you have another equation, right? This is going to overlap at 5, right? So I will mark it from, so this is going to, the third equation is going to overlap at 8, right? So from 8 to 10, you have another equation, right? And 10 to 15, you have another equation, right? So basically the second equation and first equation, we should give you the same value at 5, because those two are valid at 5, right? So between my x is going to be less than 5 and greater than 0, right? Here it's going to be 5, right? 8, right? Here it's going to be 8 to 10. It's going to be 10 to 50, right? I hope it's correct. So x. So my equation was bending moment m is equal to, so this is m, right? So m is equal to how much? Remember 10 point minus 10.9 plus x cube over 6, right? So that was my equation. So I can't write that equation, right? I have to go there and directly paste it to here. So between x2, so what I'm going to do is minus 10.9 9 into x, right, into x plus x squared, right? Same b2 x squared to the power 3 divided by 6, right? That's my bending moment. Yeah, can you see? Right? Yes, I will use it because it's easy to construct the equation from far away. And yes, it's like, okay, yeah, 10.19 x plus x to the power 3 over 5, right? So that is 6 is equal to 0, right? That's okay. So you can drag that until 5. So at 5, you can see it is 33.66. Just take it here, right? So I need to check second equation. Second equation was 10.9 minus x plus 12.5 into x minus 10 over 3. We'll start it from here. X plus 12.5 into x minus 10 over 3, right? So that's going to be the same answer, right? So it's going to be because at still the bending moment is continuous graph, right? Am I right? X minus 10.3, right? Yes. I can until 8, right? If you want, you can do it here. But here something interesting happens. I'll show you. So can you see this equation is exactly same as this part. What the difference is, as soon as it passes 8, it reduces to 20. This part is almost same, right? Here, you can see. So what's going to have happen is, so if you have something like this, there's a jump here, 20, right? So I will take it from the 8, okay? That's why I did not continue to 8, because here it is not continuous, right? There's a jump due to this bending moment. If you like, so if you ever encounter any bending moment, your bending moment diagram, like this kind of jumps it will have, right? Not continuous. Other than that, it should be continuous, right? So you have a jump here. Can you see this from the equation? The same equation, now we are reducing 20, right? So you can just construct this at 8. You can check this, and same equation, you have to minus 20, right? So you can see until 10, or can stop it from 10. 10, that's okay. At 10, you have what? This is the equation. So this part is going to be same. So for that part, you add 3/2 x minus 10 to the power 2, right? Is that right? This is x and x minus 10, x minus 10 over 2, yes, 1.5 into x minus 10 to the power 2. You add it. So the equation, you add 1.5 into x minus 10 to the power 2, right? That's 1 over 10, x minus 10 to the power 2. That's you're going to add it. So that's going to be the same, right? Even if you didn't add it. This is your value. So you can see it's almost 0, right? It should be, because at the free end, it should be 0, right? So you can just go and draw this now. Let me draw this. Can you see? This is your bending moment diagram, right? Bending moment, and just so this is actually bending moment. So your job is not to draw this, right? So you can just use Excel and draw this easily. X distance, right? Right? So you can see our sign convention is clockwise. So if you consider clockwise or two, I taught you at the first video, we are taking Hawking positive, right? So in the nowhere in this beam you have a Hawking moment, right? So at 15, right? 0. Okay, so this is your bending moment, right? So yes, marker. Right. Okay. So this is your bending moment diagram, and yes. Okay. So it is entirely sagging bending moments throughout the beam, right? So you can see it comes to global minimum, local minimum, right? Local minimum at x equals let me say 5 or something, right? Yes, 4.7, right? Then it's going to reduce. Why? Here, so now you need to analyze what is actually in this, right? So you just draw and see, and it is not going to be fine, right? You just say, okay, I draw the bending moment diagram. No, you are not. You are not fine, right? So you can So again, what did I do was just consider these equations between. So this is 10 minus 10.9 to x plus x to the power 3 over 6, right? So that is valid until 5, right? So even at the 5 it is valid, right? It's the same. So from the 5 you have another equation, right? It's this 10 to the power x into, so x is this cell, right? So I have formulated it using Excel. Because this equation is valid until x is equal to, sorry, x is equals to 8, right? So then you have another equation. You can formulate these values, calculate these values. So your job is not to draw this, right? But to understand the concept. So I can just take snip and try how to interpret this, right? That's something you can do rather than just drawing the bending moment diagram for different loadings, right? So when I draw that curve with x, so I'm getting entire thing is negative, right? So you can see entire scene is negative, right? Entire bending moment diagram. So how will you interpret this? So in this region from up to 5, right? You can see you have this kind of loading in the bending moment diagram. So that means, so the bending moment increases, right? It should be, because why? The load is increasing, right? So load continuously try to bend the beam, right? So there's no stopping that try to bend the beam. So the beam's resistance is also increasing with that part. So you can see it's come to local minimum. So that's not the global minimum. Local minimum for this part, it's the minimum. That's why I said local minimum. So local minimum around here. Why it's now suddenly uh, try to the negative value reduces. That negative value reduces, right? So that means in this region you don't have any load, right? So that means it's not going to affect, but you can see the effect of this load in ending here is giving an effect such that the bending moment is slightly now reduce its magnitude, right? So after you reach here, you have what? A clockwise bending moment, right? So if you have something like this, right? Clockwise, right? So that's going to again sag your beam. It's a sudden sag. Sudden sag. So if you go to here, right? So you know uh, at the ends, right? At the ends, you should have a zero bending moment. Why? There's a pin support, right? So now your resistance, so you have gone the halfway through this beam, right? So you can come it from here, right? So due to this loading up to 10, so the same way like this, right? It's going to bend this beam in this way, right? So load is uniform, right? So load is uniform, right? So that's why you got something like this curve until it's 10, right? Here also within 10 to 8, your bending moment reduce its magnitude. Why? You don't have anything, right? So it's the effect is going to reduce gradually. But from here to here, you have a loading, right? Don't think it from here. You will confuse. It should more more reduce. No, think it from here after you pass the halfway of the beam, right? So thank you.